So now we can expand, because we've split up both the fields and the momentum, so we're able to expand. So let's go back to the thing we wanted to expand. So we had this guy. And we wanted to expand it, and now we know how to expand it. We've set up a nice way of doing the multipolar expansion by introducing some additional notation. So because of what I just said, you can think of the covariant derivative, and because of what I said last time for the gauge field, we have a very simple decomposition for the covariant derivative. It's the sum of a collinear kind of piece and an ultrasoft kind of piece. So this p mu plus I partial mu is just this, and the split of the gauge field into these two pieces is what we talked about last time. And that split of the gauge field actually led to some things that we didn't talk about that we'll talk about later. So if we now look at the components that are appearing in here, we can figure out what to keep in each case, and it's pretty simple. Well, for the plus, there's nothing to drop. We just keep everything. And there's also only one type of derivative, so we just keep this. This is exact. All terms here are order lambda squared. For the perp, we just keep the collinear parts. So if I write out the other part, just for completeness, we can drop those terms relative to these terms, because these terms here are lambda, and these terms here are order lambda squared. So we drop these guys for the leading order. And then similarly for the minus. So here, this guy is order lambda squared, and this guy is order lambda 0. So we drop this guy. OK, so now just plug those things into our Lagrangian. And then we get the leading order Lagrangian. All of these phase factors can be encoded in an overall phase factor. We get the full n dot d derivative. But for the collinear parts, we only get this piece, and the piece over there. And so you can think of that as a collinear covariant derivative. So, So sort of in the obvious notation, we take the two pieces that are collinear and put them into a collinear D, and likewise in the n bar direction. OK, so this Lagrangian here is the leading order Lagrangian with this additional notation. And if you like, we have this kind of D that has both pieces in it for the n dot direction. And then for the other two, we just have the collinear pieces. And that's the leading order action. where we've carried out the multipole expansion, it just became, after we introduced the notation, it became something trivial. Okay, so the power of the notation is that once you've swallowed it, everything else is simple. If I want to go to higher order, I just work out what these terms are. Then I should also worry about these terms, and we'll do that later on. Okay, so what can we note about this? Well, one thing that we worked out earlier was that this should be of order lambda. And that actually implies that our new field, there's nothing, we were just pulling out phases, and that doesn't change the overall power counting. So our new field is of order lambda as well. And likewise, before we sort of had a power counting for the measure, which you can think of in our new notation as a power counting for this thing. And that just scales like lambda to the minus 4 as before. So all the power counting that we were doing, even before we sort of figured out what the right field to use, that all carries through, and that's why I did it earlier. Okay, so what's going on here, which I didn't really spell out, but I can spell out now, is since this phase is order 1, the power counting for momenta induces a power counting on the x. And it's kind of the larger momentum that dominates, so x minus scales like 1 over p plus, x plus. Remember, in the dot product, it's always plus times minus. The confusing thing about light cone coordinates. And so if you count up the powers of lambda, you get minus 4 of them, because you get two here, none here, and then 2 there. So that's all going through as before. And then if you ask, what's the order of the Lagrangian? The Lagrangian density here is order lambda to the 4. Because we have 2 fields, and then we have a lambda squared here, and then a lambda here, a lambda 0 here, and a lambda there. Okay, and our power counting made that explicit, so the whole thing is lambda to the 4. This lambda to the 4 of the Lagrange density cancels the lambda to the minus 4 of the measure, and you get that when you integrate, this is lambda to 0, and that's what we wanted. That was our convention for the leading order term. Okay, so the power counting nothing really changes. We had a power counting for momenta. We just now have a power counting for all these objects that we're talking about. What about locality? Well, all the fields in this Lagrangian are at x. So it is local in the residual momenta. We said that already when we were drawing Feynman diagrams, and that's just true of the action. And so what that means is the action is local at the smallest momentum scale in our problem. And we would have been surprised if we'd encountered anything different than that. The action is actually also local at the scale lambda. Even though we adopted this label convention just to separate the momenta, there's no inverse perp derivatives in this action. And so the perp derivatives appear in the numerator, and so it's actually local at that scale too. And so if you like this, we've just written something that's in momentum space, and it's the momentum space version of locality at the scale lambda. And we've hidden all the momentum space, so it even looks local. But if we were to write out the indices, again, we would see that it's the momentum space version of locality. And so the only scale that it's non-local at is actually the scale that we want to integrate out, the hard scale. And that's due to sort of the presence of this kind of 1 over m bar dot PL type factor. Okay, so that we already sort of saw earlier when we were talking about building up the Wilson line, right? We said, well, there's some off-shell fields, let's start integrating them out. And we got inverse powers of this m bar dot PL. But that was at the hard scale, so we had no choice but to integrate them out. And you can think about this factor here. If it bothers you, you can think about it in the same way, that it's not any worse than what we already did. OK, let's see if this Lagrangian does what we want. Let's look at propagators. If we have a collinear propagator with a collinear gluon, say, coming in, let's look at this diagram. These are fields in the n direction. This is some guy that's PL, PR, and let me just take it to be PR plus for convenience. Then if you look at this guy and you ask what that propagator is, it comes out exactly how we want it to come out. So there's nothing that gets dropped in the denominator in particular. In the sense that all components of the momentum are showing up. We're still dropping residuals, but if we're just talking about collinear particles, then the residuals are kind of redundant. The purpose of the residuals momenta is when we're talking about both collinear and ultrasoft particles. So the other case that we need to treat is when we have an ultrasoft particle. We could, of course, have both of them at the same time, but let's treat this case. So we have PL, PR plus, some K, which is purely residual. And now this guy, because of the derivatives, these derivatives don't see the K. None of these derivatives see the K. So in the n bar and the perp, we don't see the K. And it would look like that. Okay, if you want to make it kind of look more like the Lagrangian and convince yourself that this is the inverse, just divide by this factor. Divide by this factor, then it puts it under here. And that's exactly what this is doing if you ignore the Dirac structure. It's not playing a role, really, for the propagator. Okay, so and same here. If you take this factor, divide it out, then you get the plus piece, which is this derivative. And then you get perp squared over minus. And that's what happens if you put this downstairs. Okay, where for collinear, all the components show up because we didn't drop anything. For ultrasoft, only the plus shows up, because it only changes the plus momentum of the collinear field. Okay, so the Lagrangian is smart. It knows how to deal with the fact that the propagator should be different for these two situations. And that was one of the things that we wanted, and we achieved it. So even though the Lagrangian doesn't know what's going to happen, it's smart enough to deal with any possible thing that could happen and give the right propagator. And we don't have to expand any further. The Lagrangian knows how to give the leading order propagator for any situation that we might be interested in a leading order, which are these two situations. What about Feynman rules for interactions? So that's also interesting. So if we have an ultrasoft gluon, and let's say it has an index mu, there's only one term that comes in, because it's only the n dot d that had an ultrasoft field. All the other ultrasoft fields got dropped. So there's only n dot a ultrasoft in the LCC0. And so there's only one term. Things are a little more complicated for the collinear. And this is kind of the price that we pay from setting up the notation that we did, the way we did. So this guy here has all terms. Just by pulling a gluon field out of any one of the terms. Can couple to any component of the gluon field, just like in QCD. But our Feynman rule is a little more complicated because of the way we set things up. And in some ways, what's happened is that we've made the propagator simpler for the collinear fields at the expense of complicating the interaction. Okay, so we couple to all components, the perp component, the n component, and the n bar component, if this is a collinear field. So those are all collinear fields. So one way of thinking about why that kind of had to happen is the following. What if we didn't have ultrasofts? Imagine that we were going through this whole story, but we just had collinears. Then you wouldn't really need to go through this multipole expansion, because there'd never be two momentum of different size. And you could actually just, for the collinears, use QCD. The purpose of having this multipole expansion is really because we want to talk about both of these things at the same time. In fact, if you only had collinears, you just boost to the frame where they're not having this boosted scaling. It's really relative scalings that the effective theory is trying to encode. The relative scaling between collinear and ultrasoft, or between, say, two collinears going off back to back. That's where the power of the effective theory is, in relative things. So it's only when you have two things at the same time and you want to describe both of them that you get into the kind of complications we're talking about. If you just have one thing, then things are simple. You could just use QCD. But if you just had QCD for the collinear sector, you'd know that you have a very simple Feynman rule, I, G, TA, gamma mu, and a more complicated propagator, because you'd have a p slash. Well, here we don't have any p slash. The propagator, if you write out the spin, is simply n slash over 2. But the p slash has to come back somewhere, and it's coming back because it gets encoded in the way we set things up in this vertex. So these factors of p slash here are just reproducing p slashes that in the full QCD context would be in the propagator. And it's you can actually work out if you start writing down Feynman diagrams that that's exactly what's going on. Okay, so that's kind of the price that we paid for sort of making a Lagrangian that dealt with both things at the same time and made this part really simple. That part became slightly more complicated. But once we know what I just told you, we can oftentimes carry out calculations here by making correspondences with the full QCD Lagrangian. Sometimes that's done. Anyway. We couple to all four components of the field. Actually, once you start learning how to deal with numerators like this, it's no more, it's different than what you're used to, but it's just in some sense as complicated using this Lagrangian. It's just that you're writing things out in components, which you might not want to do, right? Why decompose things into components, which we're doing here? Why do that if you don't have sort of something that's projecting onto a component? That's in some sense the only complication. Okay, and there's one other thing, of course, which is that the Lagrangian also had terms like this. So it's not simply just one gluon interaction. There was also, we could have, for example, two covariant derivatives, two of these perp covariant derivatives, for example, and there's a Feynman rule for that too, which comes out of the action that we wrote down. Okay. Questions?
So I guess that this, your effective theory is reproducing the collinear and soft divergences of QCD.
It is, yeah.
So like in ordinary QCD, the IR divergence cancel with the interference with one loop diagram.
And that'll happen here too.
And you have to go to like loops, or it's happening like a leading order?
No, you have to look at loops too. So yeah, there can be cancellations between real and virtual graphs. And there actually can be such cancellations separately for ultrasoft gluons and for collinear gluons. So we'll talk about what you're talking about a little later on. But there is an important point that I'll emphasize since you asked the question. If you ask about the divergences, the infrared divergences of an ultrasoft gluon, so the ultrasoft gluon, if we go back to sort of where it was living here, collinear gluon was living here. And if you ask about divergences, what the divergences are coming from are momenta going to 0 or momentum going collinear. And this guy here that lives kind of here can go both collinear and it can go soft. So the names collinear and soft, which correspond to the names collinear and soft divergences, are not a one-to-one correspondence. A ultrasoft particle can actually have both collinear and soft divergences. The collinear particle can also actually have both types of divergences. And so the names are associated to where they live in momentum space, not the type of divergences that they're encoding. If I wanted to do something along the lines of setting up the field theory to just exactly correspond to the divergences, well, first of all, no one's ever figured out how to do that. But you can imagine how it would be different than what I'm doing, because if I wanted to do that, then somehow my collinear field should be sort of sensitive to angles. It should be like an angular variable, because the divergences are coming from angles going to 0. And it's not an angular variable, it's just a regular field. So setting things up in this way is kind of how we usually think about effective field theory. We're just talking about momenta small or big. And that's what we're doing, but it comes in the sense that you don't have a direct correspondence with the divergences.
So you have more divergences?
The way of saying it is that you have more divergences in a way, but they're the same divergences. Well, yeah. So you don't have more divergences, but really what's happening is, so if you look at this kind of picture, you could actually have, if you look at the kind of infrared divergences that you could have, so let's regulate them with an off-shellness. You could have infrared divergences that would be like that. But there's also, when you do some diagrams, there's kind of infrared divergences that could look like this. OK? I'm just telling you something that you'll have to trust me. And this is like coming from an ultrasoft scale. P squared over P minus, that's this hyperbola. That's the scale of this hyperbola. And the P squared here is the scale of this hyperbola. What the effective theory does is any ultrasoft diagram, that'll give all these logs. Any collinear diagram will give all these logs. And since you could say, well, P minus is a hard scale, so really only the IR divergences are just P squared. But the effective theory is kind of dividing it up into these two types of logs, and that's actually going to be useful for us. We'll see that allows us to do some things that are not so obvious how to do in the full theory. OK, so yes, it is kind of splitting an IR divergence in these two different types of terms, but that's actually going to be something that's useful because in some sense there's two physical scales in the infrared. There's this sort of collinear hyperbola and the ultrasoft hyperbola, and the effective theory is making that explicit. Other questions? All questions have been good so far. Keep asking.
Could you try using two different lambdas for the ultrasoft and the collinear?
Yeah, so you could if there was a physical reason why you wanted to. And the thing is that you would have, if the lambdas overorder each other, then there's no point. If there's a hierarchy, then what that would change would be that the n dot d should get expanded too. But if the n dot d gets expanded, then kind of what is happening is you're really decoupling everything. Yeah, and so you're kind of losing the dynamical connection that we have so far in this theory. So I think it's not so interesting, but it's worth thinking about.